When we look at a vacant construction lot, it is easy to see a blank canvas, but the ground beneath that site is not finished settling. It is actively participating in a continuous geological cycle. This brings us to geomorphology. It is the scientific study of how topographic features originate and evolved through physical, chemical, and biological processes operating at or near the Earth's surface. For a civil engineer, understanding this science is an absolute prerequisite. Every critical phase of a project, from the initial site investigation to groundwater hydrology and foundation engineering, is dictated by these exact processes. This flowchart maps the exact relationship between the Earth's surface and structural design. Notice the direct nodes connecting engineering geomorphology to soil mechanics, which then feeds straight into civil engineering design and construction. When we account for these geomorphic variables, site investigation moves from a snapshot of the present to a projection of the future. A project's stability is inherently tied to the ongoing geological forces acting upon the foundation. Earth's topography exists in a state of dynamic equilibrium. It is caught between two competing energy systems, endogenetic and exogenetic forces. Endogenetic processes are the builders. They are powered entirely by the Earth's internal planetary heat. Looking at this cross-section of the Earth's structure, you can trace the origin point of this internal energy. It radiates outward from the high-heat iron zones of the core and up through the silicate materials in the mantle. Opposing them are the exogenetic processes. These are the sculptors, driven by external forces operating on or above the surface, primarily solar radiation and gravity. Every construction project on the planet sits in the crossfire of this dual energy engine. It is constantly being pushed up from below and torn down from above. To accurately model these competing forces, we need a rigid taxonomy that classifies every geomorphological process on the planet. This chart provides that master system architecture. At the highest level, it separates extraterrestrial impacts, like meteorites, from terrestrial planetary mechanics. Drilling down into the terrestrial branch, we hit the hard dividing line: exogenic processes operating on the outside and endogenic processes operating from within. Categorizing a specific site's active processes into this framework is the first required step to calculate its long-term physical stability. Let's examine the builders first. The endogenic system generates its internal power through radioactivity, rotational and tidal friction, and the primordial heat left over from the Earth's origin. That deep thermal energy physically translates into severe crustal deformation. Immense lateral pressure forces flat layers of the lithosphere to buckle and thrust upward. This heat yields two macro deformations: orogeny, which is severe folding in mountain building, and eperogeny, which is the broad uplift or warping of massive continental plates. This diagram shows how these structural movements alter the rock itself. A magma chamber radiates intense heat and pressure, triggering contact metamorphism. This physically changes the hardness and crystalline structure of the surrounding rock layers. Because crystal thickness and heat flow vary, the action of these internal forces is not uniform. They produce a tectonically controlled crustal surface that is highly uneven and prone to faulting and fracturing. Ultimately, endogenic forces are responsible for creating massive potential energy in the form of elevation and relief. That elevation is the initial kinetic load our structures must contend with. Once that elevation exists, the opposing forces take over. Denudation is the umbrella term for stripping off or uncovering the Earth's surface, driven by thermal climate gradients and gravity. This flowchart illustrates the strict chronological sequence of the denudation pipeline. It begins with weathering, moves downward into erosional activities, through transportation, and finally terminates in deposition. A common engineering pitfall is treating these stages interchangeably, but you must distinguish exactly between weathering and erosion. This side-by-side comparison highlights the critical variable: movement. Weathering is the process of disintegration, where rocks stay in the exact same place. Erosion is the decomposition of rocks that are then actively transported somewhere else. Knowing whether a rock face is merely weathering in place or actively eroding changes the entire mathematical approach you use to calculate retaining walls and load-bearing capacities. Let's look closer at weathering. It is strictly an in-place breakdown. This occurs mechanically through physical freeze-thaw cycles expanding cracks. chemically through acidic rainwater altering minerals, or biologically through root intrusion splitting the structure apart. Looking at this illustration, you can observe the mechanical reality of weathering. A solid mass loses its structural integrity and fractures into smaller pieces, yet the material itself remains entirely stationary. To move into erosion and transportation, the system requires an active mobile agent to apply kinetic energy to that weathered material. This grid catalogs the primary mobile agents dictating that transport: running water in rivers, wind across arid environments, moving ice masses in glaciers, and wave currents in coastal zones. This transport pipeline leads to two opposing vertical outcomes for any given site: degradation, which is the lowering of a surface, and aggradation, which is elevating a surface through sediment deposition. This split-screen diagram compares the mathematical net results on a site's baseline. On the left, degradation actively removes material, shedding its top layers and lowering the elevation. On the right, aggradation does the exact reverse, stacking new sediment and raising the bottomland surface. Because of degradation and aggradation, a site is either actively losing mass or gaining it. Baseline elevations in civil engineering are never permanently fixed. This brings us to the most immediate geomorphic threat to civil engineering: mass movement or mass wasting. It is the direct gravitational transfer of near-surface soil and rock material down a slope. As this slide demonstrates, mass movement operates on a massive spectrum of velocity. It ranges from a very slow microscopic creep seen in the diagram to the near instantaneous slope failure blocking the highway on the right. These gravitational transfers are generally viscous processes. They are facilitated by water infiltrating and acting upon previously weathered, weakened rock. The physics of a slope failure are absolute. The exact moment the downward gravitational shear stress exceeds the internal friction and cohesive strength of the saturated material, the entire mass shears downward. Mass wasting is the highest stakes intersection of geomorphology and engineering. Failing to respect the mechanics of these denudation processes will result in total structural destruction. We can now synthesize this entire dual energy engine. Endogenetic forces push the crust up to create potential energy. Exogenetic forces break it down to release that kinetic energy. Here is the cycle operating simultaneously across a landscape. The jagged endogenetic peak actively wears down under exogenetic forces, and the resulting sediment flows down a river system, eventually fanning out into a wide delta through aggradation. The isolated samples analyzed in a soil mechanics lab are snapshots of material paused mid-transit in the denudation pipeline. To accurately characterize geomaterials, you must deduce where the soil came from, what agent transported it, and exactly where gravity intends to drag it next. Designing for the long term requires a continuous negotiation with the Earth's surface. Every successful structure is, in effect, a calculated pause in the work of a relentless geomorphic engine.